error correction, but we somehow stumbled on some subsidiary thing, which is what I'm going to talk about. Okay, so the title is Bulk Locality and Asymptotic Causal Diamonds, and so let me start by giving some general introduction on why it might be interesting to look at causal diamonds in the first place. So holography is likely to be a universal feature of quantum gravity. So this is a premise that I'll start with. And in what way it is realized, etc., it's a different question, but at least let's start with that premise. And there are two reasons to think it, at least two reasons to think it. One of them is that there is no local observable in a diffinvariant theory with a dynamical metric. This is something that we expect in a quantum mechanical theory, which is diffinvariant and has a dynamical metric. And we also know that from the existence of black holes in the theories of gravity, that in a region, the entropy in a region scales with area and not volume. So these are fairly, heuristic statements. But both of these are, the fact that a diffinvariant theory with a dynamical metric that contains black holes, that could very well be the definition of a theory of gravity. So which kind of suggests that at least from the get-go, there is hints of holography built into what one might want from a theory of quantum gravity.
Chethan, this statement about entropy is in the sense of a bound.
Right, right, yeah. So, but it's one thing I want to emphasize, it's supposed to be a micro-canonical type of bound. So it's really counting somehow the degrees of freedom. This is one of the things that Busso likes to emphasize. And in the sense that there is a time reversal in the causal diamond or something like that, that he argues that it is really counting the degrees of freedom inside the region. This is one way in which he likes to phrase it. So, I mean, I'm really not an expert on this. So the precise bound is by putting these light sheets in a region, and then the boundary of that region has an area, and that area bounds the entropy that goes through the light sheet. So that's the statement as far as I understand. Yeah. So
sorry, just to.
Yeah.
So let's just suppose we take Minkowski space.
Right.
We take some region.
Right.
And then we draw the upward diamond.
Yeah. So I think the way in which it is constructed is typically by starting with a point and constructing the region that it covers. So because if you start with a region, it's not super clear to me that it will actually close. Okay. So maybe there is some subtleties there. But the way in which I understand is that you start with the point, then the backward light cone is well defined, and start at the point, the future light cone is also well defined. So the intersection has a well defined area. Okay. So the intersection of the boundary of the intersection, the waist of the causal diamond. So that is bounded. That area it bounds the entropy that will pass through this null cone. This is the picture. So yeah.
I'm sorry, just this level to talk about the first question. As theories of gravity often have well-defined asymptotics.
Right.
And then you can define almost local observables by shooting geodesics from asymptotics
right.
to a certain distance.
Right.
Say the operator where that geodesic ends. As is done in ADSA.
Right.
When people want to try to construct local operators, roughly that's what they do. So it's not so clear to me that
what is in contradiction? I mean, is it a contradiction or?
No, you say that there are no local observables in the invariant theory of gravity, which implies sort of holography. But there are almost local observables, right? Or not?
What do you mean by almost local observables?
Suppose we are in ADS. We start at the boundary of ADS, and we label a point by a geodesic direction, a point to the boundary from where geodesic starts.
Yeah. Yeah. So you can label points through that. Yeah.
We can label points through that.
Yeah.
Just to understand, sorry, where you start and how far you go.
How far you go, where you start, what angle, and how far you go.
Right. Yeah.
Okay. Now, when you're doing a path integral over matrix, you want to put O of x. So you label O by that information. Which, when the metric is not fluctuating very much, would be at a particular point.
Yeah, but but that if the metric is not fluctuating, then you can always do that, right? I mean.
But if the metric is fluctuating also, this is a well-defined observable. I'm saying that as many observables as if the metric was not fluctuating.
What is that? I mean, I'm not understanding.
You use affine time, which is okay. There'll be some issue of how to
normalize it.
Let's
say we fix some conventions.
Yeah.
So I'm saying that you can label operators. I'm saying something obvious.
Yeah. So, but it's kind of, I think the question is one of on shell versus off shell maybe. So in the so if you want to, so I suspect it might be. So I mean, I'm just saying something very basic in some sense. I think you're talking about something maybe a little more profound. So all I'm really saying is that the metric, the metric is fluctuating, and how do you label a point in space if the metric is fluctuating and it's diff-invariant? It's just that.
Yeah, and I'm giving you a way. I'm saying that suppose your metric does not fluctuate at the boundary, which is what we assume.
Right.
Theories of gravity.
Right.
Then you can label points by boundary data. By
Right.
starting from the boundary, finding a geodesic, choosing a point, choosing an angle, choosing a distance. That
Right.
labels points.
Right. So, but wouldn't that be a holographic description though?
If you call that holographic, I'm saying that as many observables that way as there were boundary bulk points.
Yeah, sure. I mean, but that's still consistent with what I'm saying, right? Yeah. I can't. So I mean, all I'm basically saying is that if you have a fluctuating dynamical metric which is diff-invariant, it's the location at which the metric is, well, so yeah. I guess what you're saying is that you,
I mean, it is conceptually at least an important point as to whether there are well-defined operators which in the semi-classical limit become local operators,
right?
but nonetheless have an exact definition in the full quantum theory. I mean, that's what.
So, yeah. So I agree. So, but I mean, I'm just not seeing what is the conflict. Right?
But I thought you were going to say that because all observables are area observables, that's why holography.
Oh, no. Yeah, so these are, okay, so you're saying that the first statement and second statement have a slight tension between them. Is that what you're saying?
I'm saying that, holography is often worded as saying that the only good observables in quantum gravity are on some slice at the boundary. And that's holography.
No, that's not necessarily what I'm saying. So, in fact, the idea of causal diamond that we will introduce is precisely so that somehow you have a way to access information inside the bulk for some single observer. So, this is the idea that...
Yeah, I'm sorry for disrupting.
No. So anyway, so I think since the discussion came up, so maybe one should also say that in the G Newton going to zero limit, you basically have, so the one obvious way in which you can label space-time positions is that you take the, when G Newton goes to zero, you have a fixed background metric, and in that metric, all the points that are related by diffeomorphisms to that metric give you a way to label points, label a point on the manifold, and that gives you a fixed background if you want. And so what you do, for instance, in flat space is basically that if you do a coordinate transformation, so your metric that you start with is, you go to a frame where the metric is, the isometries of the metric are manifest, and then you have a way to label, let's say in eta mu nu you have x, y, z, t, and the labels of the coordinates in that coordinate system basically label points in spacetime. That's one way to look at the G Newton going to zero limit. Yeah, so in other words, the cruder semi-classical features of gravity almost seem to indicate holography is possibly a universal feature.
If you used Eddington-Finkelstein coordinates for
Right.
ADS, you're doing exactly what I said.
Right.
Flat.
Yeah.
Leveling it very
Right. Yeah. So I mean, so for instance, I will be using bulk reconstruction in the standard sense of ADS Riller wedge and all that. So this is kind of like, in fact, that is kind of where it is going. Okay. So yeah. So now that I have not mentioned the word ADS yet, and holography as a key feature of quantum gravity was maybe introduced as a qualitative idea long before that by Tooft and Susskind. And what makes ADS CFT shocking is that it's an explicit quantum gravity is known as an ordinary QFT, and the next feature in some sense is that the semi-classical level we have a dictionary for relating bulk calculations to boundary calculations, and this is the realization in some sense that this quantum gravity, the first line here, is actually a holographic theory, and if you believed in holography, maybe it was not so shocking to begin with. So okay. So if we did not know about ADS-CFT, what is the most natural structure which might help us in understanding holography? So a good candidate perhaps is a causal diamond. And the idea here is that it is the largest region in space-time that can be causally probed by a single observer. So that's roughly what I think Shiraz was saying, which is that you can, if you draw a picture, so a causal diamond is schematically like this, something like this. and it doesn't have to be in flat space or anything. So some trajectory that goes like this, if you, so you can send in information from here and get back information from here. And so it's the maximum region that can be covered by a time-like observer, and that's basically what a causal diamond is. So the statement is that the entropy inside a causal diamond is bounded by this A by 4G of the surface area of that region and surface area of this circle or sphere here. And no counterexample is known as far as I know, including in cosmological spacetime. Both these features have a flavor of holography. So these are the reasons why we would like to understand.
Can you say again, you were saying something about what Musa says, but can you say again, what do you mean by the entropy inside a causal diamond?
So if there, let's say there is some stress tensor or something that is flowing through this region. So the entropy of that, entropy of the matter that crosses this, entropy of the matter and the gravity that is inside this region, the bound for that is basically given by the area of this thing. That's the statement. So if there is some stuff inside, it will have some microcanonical, let's say, entropy, and that entropy is bounded by the area of this cross section. This is roughly what it means. So yeah.
If one wanted to make this a precise statement,
Mm-hmm.
a statement about entanglement entropy.
No, I think it is I think it is
This
thermal.
level it's classical,
Yeah.
but I think the idea would be that there's probably some generalized version.
Right.
Would have to be-
Entanglement entropy.
Which is divergent and then
Yeah.
But-
so
but-
I had a similar question. Without entanglement entropy, I don't understand this.
So for instance, you can put like, so the simplest way to do it is, let's say there is like some sort of radiation or something. So radiation, black holes, all of these things, it can be inside, but they will all have appropriate entropies, right? I mean, so this is just basically the Chethan Boltzmann type of entropy. All of that is contained in this region, so that you can just sum.
So let's say that that's a fixed time slice
Uh-huh.
in the diagonal of the diamond,
Yeah.
and so that's a subregion of the whole space.
No, so I'm saying that this whole region is like the things are moving through here, right? I mean this is just some space. This is the space-time region, and this region is, let's just make it flat space. So there are time-like trajectories going through this thing, and these time-like trajectories are trajectories of, let's say, matter particles, or even if you treat it as, if you include null things also, then there is also radiation, and all of that you can assign density from its equation of state and that sort of thing. So, and if you do that, and you have the other possible object is a black hole, or black holes, and so the sum of all these things that can pass through this light sheet here, so that its entropy is something you can just write down as an integral or sum or whatever.
No, wait. How do I assign it? How do I assign a state to a particular subregion? I mean, or a mixed state.
Yeah, sure.
He's saying throw in tea, coffee, gas molecules, everything. They'll have some entropy inside. The maximum entropy that can be contained in the region is bounded by the end.
Yeah.
In the spirit of Wittgenstein.
But okay, so I'm trying the tea, coffee, etc. I have changed, perturbed the initial wave function of the whole space-time into something else now. Okay, so now there is some wave function. Or density matrix, whatever. Now I have a subregion. Okay, how do I assign an entropy to the subregion? I understand what's being done. So I'm perturbing the initial wave function or the initial mixed state of the whole space-time. Okay, for the whole space-time, I would rather have used Vegas, whatever. So now, how do I assign entropy to a particular subregion?
Okay, so we can come to the more precise version in terms of entanglement. But zeroth order, I think what Chethan is saying is, how do you?
This is something from about 20 years ago, which is long before entanglement. It's basically just old school.
It might be in a pure state, but it looks in some region close to thermal. You say, okay, this is the local temperature. That, I think
Yeah.
that's the
I mean,
then you try to
Yeah, I mean, so I also have to say that I am, I should.
Around this subregion, or what do I do? I mean, it's an open system. I mean, the point is, this subregion thing is an open system. There are no walls. There are
I mean, I have not looked at it in too much detail. So you know, as I said, it is the stuff that I'm going to say is this is not a fully cooked talk that I have to first tell you. So this is not a fully cooked talk, and this is right.
Maybe my shortcoming.
Yeah.
Then also I didn't quite understand what was
So yeah, but
it's in the same spirit in which we talk about black hole thermodynamics, right? When people, we can come to the more precise version in terms of entanglement entropy, but when we talk about a second law for black holes, including the entropy, what do we mean, right? We mean take the entropy of the stuff that falls into the black hole plus the area of the black hole. You know, that always satisfies the generalized.
for instance, I mean, in a Robertson-Walker spacetime, there is a notion of an entropy,
maybe
right?
the entanglement entropy part, which is like four-dimensional one contribution, maybe that is less.
Yeah, so the more precise version is that you keep track of the density matrix. You compute trace log rho. That's going to be divergent. And then you have to wave your hands, but the standard waving of hands is G Newton also suffers a renormalization. One infinity cancels the other, and therefore you still get in terms of the.
Yeah, I think that's probably the more precise way to say it, but I don't think Busso even goes that far. I think what he just does is that in a given space-time, for instance, in Robertson-Walker, you talk about the entropy of, for instance, radiation. So you can talk about, so that's the kind of thing that he's counting. So he just, you know, I think he integrates it over the cross-section over, basically, so this is the part which I have not really looked at it in detail, but the claim would be that the entropy that passes through this light sheet can in some sense be integrated. And so that is bounded by the area here by 4G. That's the statement. So,
There
yeah.
were more precise statements, right, by Cassini and Maldacena and company. There's this claim proof of the Busso bound that makes a statement about entanglement.
I thought that was a weakly coupled quantum field theory. But here the statement is in some sense for generic spacetimes.
Weakly coupled quantum field theory coupled to gravity.
Yeah, but I think, but there is,
Quantum field theory.
was there a gravity in that at all?
Well,
I was not very sure about that, but maybe there is, but I haven't looked at it in detail. So, so what I thought was, so this is the original statement that I'm talking
there's
about.
a paper by Cassini and Maldacena called Proof of the Busso,
Yeah, that's right.
which talks where they answer and they address all of Gautam's questions, where the entanglement comes about 20 times in the paper.
Right.
No, but I mean, roughly speaking, that is the, I mean, I haven't looked at the basic idea is that the, you know, if you talk in terms of a renormalized Newton constant, you try to absorb the divergence, right?
Right, yeah.
That's sort of where that was your point. What do you do with the divergence?
Okay, so yeah, so there is this, and yeah, so maybe I should go to the next slide. But yeah, so yeah, maybe I should look here. So why does no one ever talk about causal diamonds and ADS-CFT? But well, they do, and that's, you know, at least in the last few years. And I think so some of these papers. So I'll list some papers that I've seen, but there are certainly more. So closely related to this idea of naturally emerged in ADS-CFT, especially in the last few years. So one of them is in the context of this HKLL-like construction, where you have a boundary subregion from where you construct the bulk, the reconstructible part of the bulk, and that involves loosely causal diamond-like ideas, a causal wedge that is anchored at the boundary. And so there is another definition of another thing that has come up in these things. So I should again say that many of these things I am not super familiar with. You know, many of you probably know this better, but I just want to say that the general idea of a causal diamond or using light sheets in order to reconstruct bulk from the boundary has been of some use in the last few years. And yeah, so the space of causal diamonds, so this is, so these two are roughly closely related, and the third one is also related, but the idea is that you look at the causal diamonds on the boundary Minkowski space, and because causal diamonds in the boundary Minkowski space basically give you a sphere where they intersect like this, and so it can also be thought of as a space of spheres on the boundary, and that has you know, some amount of work has gone into this. I'll say a few words more about this. So this is largely motivation. So this can also be viewed as a space of bulk space-like geodesics. The idea being that if you are in ADS3, for instance, if a boundary region can anchor. So this is maybe my boundary here. And so let's say there is a picture like this. So this is the boundary causal diamond, and you have a geodesic that is anchored at the two endpoints of this. So this construction has been used for.
This is the light cone in the boundary.
This is the light cone in the boundary. That's right. And this curve is useful because the idea that they want to explore is that if you know the space of geodesics anchored at the boundary 2 points, then in principle you might be able to reconstruct bulk metrics. So this is the how much of the bulk do you know from this thing, and this is what was referred to as integral geometry, and kinematic space is the space of 2 points on the boundary. So
this works only in ADS3.
this specific geodesic construction, yes. So but they have the space of boundary spheres they have explored in general dimensions, and they try to relate it to bulk minimal surfaces and all that. Yes. So so there is a lot of work on this. I'm just saying the most basic parts. So these are various places where these boundary causal diamonds have shown up.
Sorry, just one more.
Yeah.
I think it's an informational question.
Yeah.
Which is that when these diamonds are drawn,
Mm-hmm.
they're drawn according to the EDS geometry.
Which one in the?
You are drawing some.
This one here.
The one in the bulk when you're drawing light sheets.
Yeah. So this one is actually a boundary causal
Yeah.
diamond.
So there's no problem.
Yeah. Right.
But I'm saying that when you are drawing, some causal diamonds in the bulk.
Yeah. So those are bulk metrics.
ADS geometry.
ADS geometry. And
But even when the saddle point geometry inside is significantly different, like a black hole.
right.
There you don't use the black hole metric to draw this.
So this, for instance, these first statements that I'm talking, So this first statement that I'm talking about, most of the stuff that people talk about, as far as I have seen, are in the background. The background is always empty ADS. It is not when the background is a black hole.
But suppose there's a black hole sitting.
Which
one do you use? Will you use black hole?
I would imagine they use black hole, but in that case, I've only seen people working with maybe global reconstruction. I'm not very sure that the Rindler reconstruction for patch-wise, subregion-wise reconstruction, I don't think I have seen an example of that, but it should work. So this is what I would imagine. Yeah.
Yeah, I didn't answer. Yeah, this is the standard reconstruction what is it? HKLL.
Yeah.
Which uses Rindler observers that in the bulk that cover a patch of the bulk, and then.
So HKL, HKLL comes in a couple of varieties. So the one is where you took a reconstructed point in the bulk. You look at all the points in the boundary which are space-like separated from it. That's called global reconstruction. And then there is another one where you start with a subregion and try to reconstruct it inside precisely this causal diamond type of thing, which you can,
That's kind of what the second thing is connected to taking a family of Rindler observers.
That's, yeah,
who have
that's
a
right.
Rindler horizon that just
That's right, yeah. So, yeah. Okay, so.
It's all done in ADS.
Even when the geometry is significantly different.
Yeah, so the examples I've seen are all in ADS, but the principle I think should work even for the Rindler wedge for the reconstruction. Okay, so a key point about these constructions is that all of them seem tied to the boundary. It is not the bulk causal diamonds that seem to have played a key role in ADS CFT, at least so far. And perhaps this is the message one should export even beyond ADS, is kind of the thing that I would like to try. In a way, these constructions seem to be capturing a holographic data associated with ADS CFT. And so they're basically capturing boundary subregions, especially this Rindler wedge reconstruction. it's a subregion of the boundary can be used to reconstruct parts of the bulk which are connected to it by this causal diamond type of picture. So, so maybe if you want to ultimately have a covariant theory of something where the boundary subregions have to be characterized in some covariant way, maybe this is a good way to start. So that's one of the motivations maybe to look at this. And since causal diamonds exist more generally than in ADS, this suggests the possibility that this might generalize to other spacetimes as well. So this is what I want to kind of look at. So okay, so a causal diamond is, let me first say what a causal diamond is. I think I already mentioned it a little bit. A causal diamond is defined by 2 points in Minkowski space, the equator of the intersection of the past light cone and the future light cone of another point is a sphere if it is not empty. And the, so this is what defines the kinematic space at the boundary of ADS. So at the boundary of ADS where things are Minkowski, so this is what people have used in order to define the kinematic space. And so a spherical entangling region seems to arise kind of naturally in many occasions, and they possibly have kinematical significance in holography. So for example, one place where I've seen this is the Ryu Takenagi proof due to these gentlemen, well, these people is for, for spherical regions. We might view this also as evidence that the causal diamond captures the kinematics of holography. So this is,
Can I ask you something?
yeah, sure.
Just about the first, when you say it's a sphere, you mean metrically a sphere or topologically? If I take one point and another displace, if I take your below point and displace it, then the intersection.
I think it is still a metric sphere. I still think it is a metric sphere. But yeah, I mean, again, this is what I believe, but it could be wrong. But I think it is the case.
But so I suppose we have any 2 points that are time-lapse separated from one another. How do we find the coordinate system so that?
Yeah. So.
Yes. Yeah.
So let us consider flat space as the first and simplest place where we might try to generalize these ideas to. In ADS, we note that the space of causal diamonds on the conformal boundary, which is Minkowski, is the kinematic space. But since in flat space, the null boundaries do not have a causal structure, the situation is less clear. You can't, what I'm basically saying is that the picture is roughly like, is not roughly, it's like this. So you don't have a causal structure on this, this asymptotic boundary. So you can't define a kinematic space by entirely working with a conformal boundary. So it's kind of natural to introduce this notion of an asymptotic causal diamond. These are bulk causal diamonds but attached to the conformal boundary of the space. This works both in ADS and flat space. So the same idea can be adapted here. And so a picture of one would be something like this. So this would be an asymptotic causal diamond here. So it turns out that they can be defined by pairs of points as well, one here, and so these are on the future and past null boundaries, and so yeah, so that's basically our basic definition. So let me work with 2 + 1 dimensions now. So if your metric is this, in the conformal coordinates, this is an Einstein static, locally Einstein static space. And so there are some ranges for these coordinates, and the metric is conformally flat and up to conformal factor, which will not be important for us. This is you know, the standard coordinate transformation that takes you to the flat space to the Einstein static patch. Okay, so these coordinates are what we will actually use for many things, which are like. So this is the picture, more or less straight from Hawking and Ellis. So you can see that there is a time-like boundary in the future. Yeah, and the spatial infinity is a circle, and so you think of if you have done a 1-point compactification on this circle here. Okay, so yeah. Okay, so the idea is one of the yeah, so the future boundary and the past boundary are defined in some way. So which means that you can an asymptotic causal diamond is just simply defined in terms of this. So you have 2 points. One, so the locations of these this and this are what basically capture this Q and P, and they're so they have some finite range from -π/2 to π/2 or something like that, and we will call these the vertices of the diamond. The intersection of the path, so the intersection between these two things is what defines our asymptotic causal diamond. So this is a picture that I have drawn on the board as well. So you can see that it's a fixed time slice. Yeah, so these are examples of causal diamonds, asymptotic causal diamonds for us. Okay, so yeah, so if you do not take these things to infinity, what you find is that these are circles or spheres in the bulk, because this is just like the boundary of ADS. So, but on the other hand, if you take it to the boundary, so you can imagine that these circles will, essentially become infinite, and you will get straight lines. So this is intuitive, and you can even you can check it explicitly. So, so the boundary of these space-like boundary of these asymptotic causal diamonds are space-like straight lines, and it is so this again has parallels with the ADS case that we looked at.
Boundary means what? It's where the two cones intersect.
So no, the boundary means the full conformal boundary.
What do you mean by boundary of the asymptotic causal diamond? On the conformal boundary?
No, I mean like if there is another dimension, this will be a hypersurface.
So that's what I meant. Where the two cones intersect is the boundary.
Yes. So this guy, and then there will be a.
It's where the past light sheet and the null.
Yeah, that's right.
Sheet intersect.
Right. That's right. Yeah. So and that boundary is basically a hyperplane or a straight line.
But sorry,
Yeah.
you're saying instead of being compact, it's non-compact? I mean, straight line meaning?
Yes, it is non-compact. Yeah.
I see. So it's quite different from that
That's right.
diagram you drew in flat space.
That's right. So in flat space, the boundaries are circles, but when you take one of these points to the conformal boundary, this becomes a straight line. So again, I mean, as I said, this talk is not really fully cooked. I keep repeating it. So one more thing I would say is that let me just finish the one sentence. So the idea is that I hope to reconstruct things inside this asymptotic causal diamond from data, some metaphysical data at the boundary. This is what I would hope to do. Okay, so even though I don't have a boundary theory, I expect that there is some data here from which I can reconstruct everything in here.
You didn't actually mean metaphysical.
I actually do mean metaphysical, unfortunately. Because so I think we can talk about it, but so the idea is that this I think essentially what Shiraz was possibly saying in my first slide, that this data can help you fix points inside here. So I think there was a question. Yeah.
The fact that it becomes a line, is this basically the point that away from a point things spread out in spheres, but if you're infinitely far away, that sphere is.
Yeah, it's roughly something like that. Yeah.
And that disk or the sphere or whatever that's in the middle.
This thing?
Intersection of the past and
Yeah.
things. It always passes through that.
No, this is not at the center. This doesn't have to be at the center. Actually, this is my lack of drawing skills. This is where, for instance, this is one, this is one, this is one.
Yeah. So this lowercase I0.
Yeah.
That is always included in that disk or not.
It is always included in the. So the point is that the I0 is just one point. So these things, these hyperplanes will go and hit them, at one point basically. So but they will always hit them, but it will hit them from two angles. So I think I'll get to that. So that's kind of yeah.
I just suppose we were in three-dimensional space.
Yeah.
As we said, if we had two time-like separated points, you could always bring them on the same time axis.
Right.
And you've got these two points. What is the canonical configuration for them? Can you put them on the same point in this circle at infinity?
I think that's what I'm going to do. So I think that So I did one count once of. So for instance, when people talk about bulk reconstruction from us on a slice where they look at the subregions, etc. So there also they have the same amount of ambiguity. Like in some, they have some freedom to boost and so on. And I did one count once, and I think that in flat space also we have the exact same amount of thing. So you can bring it to one slice. So which is basically this t equal.
One point of the circle.
What I mean is, so this slice here is where I can talk about, if I want to talk about reconstruction, I can talk about this slice in the same sense that people talk about reconstruction on a, on some t equal to 0 slice. So that's what I mean. So I think to answer Shiraz's question, I think the answer is that precisely enough freedom exists in order to do that, is what I think.
So that the intersection lies along the dotted line.
Exactly, yeah.
So in other words, you use some kind of a Rindler-like boost, in which you use some boost.
I counted parameters, so yeah, I think it is.
And the pass points are vertically separate.
I think it should be a boost. I don't know if it's a Rindler-like boost, but I think it is. Yeah, I think I have a boost and rotations are necessary.
Yeah, Rindler-like is not the right description. Some boost so that the future point and the past point are vertically separate.
That's right. So, so for instance, this picture, the one picture that I've drawn here, this thing here, is an example of what I call a symmetric causal diamond. So I expect that various things that I say about it will actually apply to even more general causal diamonds. But yeah, let me not emphasize that too much. Maybe I'm pretty sure it is true. But yeah. So, but for my purposes, I mean, it's a kind of a technicality. So I mean, it might. Yeah, I think it is a technicality that.
It just helps you to think about it.
Yeah. So. Yeah, so that's exactly what I'm. So I am going to go to a canonical configuration, but I'm not sure that I'm not 100% sure that I'm not losing physics by doing it. This is what I'm saying. Okay. So, but I'm essentially confident. So anyway, yeah. So.
So if you use the boost, then the ground state will not remain ground state.
This is all just geometric stuff. I'm not really talking yet about I'm not really doing quantum field theory in this background yet. So I'm just, so and if you do that, then I think every causal diamond I'll have to treat in some sense separately. So inside every causal diamond. So right now I'm just trying to understand the geometry of this space, geometry of flat space in terms of this. That's all I'm doing. So. Yeah, I mean, these are all probably important questions eventually, but I'm saying that before I get off the ground. So anyway, so yeah. If we consider the future and past points to be ordinary points, yeah, so this is the circles. And the difference when we take these points to the conformal boundary is that these circles end up having infinite radius and end up becoming space-like straight lines. And these are, in the language of integral geometry, these are precisely the minimal curves through which people try to slice a given piece of geometry in order to reconstruct the metric. So if you knew the integrals of certain functions through these minimal curves, in principle, can you reconstruct the entire geometry? This is a canonical question in integral geometry as far as I understand. And so this.
Say the canonical question again. If
yeah.
you knew the bulk say once more.
So the statement is that so if you knew the integrals through, okay, so the statement is that, yeah, so let's say you have some region, and you know various curves through this, and you know the integrals of all functions, I think it is all functions, through these curves. If that is the case, then you can reconstruct the function on this geometry. So this is the statement of integral geometry.
These are all geodesics.
These, in the context of integral geometry, I suspect. So in our case, what we want is we are basically trying to, taking geodesics, and the functions are effectively the metric. So what you're trying to do is you have a length function or something like that, and I think.
If you know the length function along
every geodesic, can you reconstruct the metric at each point is the question. I think this is, this might not be invertible always. So this is the standard problem of integral geometry. And my statement is only that this is a class of problems for which integral geometry is this question is well posed. So because these are straight lines going through this, so it's a, yeah.
And so your boundary of these two cones, does it hit space-like infinity?
Yes, it does. Yes, it does. So this is the kinematic space of flat space, and kinematic space of ADS was discussed in great detail by these people. And so this also means that the bulk regions that we expect to reconstruct from boundary data on the asymptotic causal diamonds are regions anchored at the boundary and bounded by these straight lines. Okay, so in ADS, if I draw this picture, so let me erase something. So
I'm a bit confused about that answer. Sorry, you mean the boundary then is two disconnected straight lines, or what?
it's just one straight line.
Well, can you show me that canonical diagram?
Uh-huh.
Seems to have one point at least,
Uh-huh.
which is deep in the bulk,
Right.
and another point can be at space like infinity.
No, so this doesn't have. I'll show you maybe I'll. So
This straight line, go ahead, sorry.
so maybe the simplest picture to draw is
Space like straight line.
yeah. So let's see this. This is the canonical standard Rindler wedge. So in the standard Rindler wedge, if it is higher dimensional, this would be a straight line that just goes like this. So, and in which case, it will come and hit this circle at the boundary, but it will hit the, because of it's one point compactified, the circle is basically all the same point. So it will effectively, I'll show some pictures which I think will make it clearer in a bit. So let me just say a couple of more things and then I'll get.
The other end is sort of intuitively also the end of the boundary.
The end of the boundary means?
At least if I had a bulk cone,
Uh-huh.
then in a 2D slice there would be two boundary points.
That's right, but it's one point compactified.
1 point, okay,
Yeah,
fine,
yeah,
I got it.
yeah.
Excuse me.
So it basically
With
go.
you, with you.
Yeah. So this also means that the
In fact, that it hits is clear from the diagram.
Right.
Because that's on that side.
yeah.
No, but I was wondering, okay,
Yeah, yeah, whether it's 2.0.
I got it now. Thank you.
So this also means what is it? Yeah. Yeah. So regions in this here we expect to reconstruct from, even though we don't have an explicit reconstruction map like in Rindler, we expect to reconstruct from the boundary. And it turns out that this so this is the picture that I'll use in order to make some comments about some structures that are similar to what shows up in quantum error correction, or my understanding of it. So we can, yeah. So this answers Shiraz's question from a little bit ago, which is that we are going to try and look at a certain canonical class of asymptotic causal diamonds which capture the t equal to 0 instant. So we want one space-like slice, and there is a similar structure that exists in ADS as well. So we want to make our picture maximally parallel, and this slice has a simple description in terms of this points that I wrote down, which is that this Q and P are related and they are the negatives of each other.
And then, sorry, just to understand,
Mm-hmm.
the statement is if you know the initial data
Mm-hmm.
on scry minus, that part of scry minus which
Uh-huh.
is in the past,
Uh-huh.
and that part of the bulk light cone,
Uh-huh.
because
So-
your thing has a bulk boundary and partly a asymptotic infinity boundary.
That's right. That's right.
But, so what is the analog of the HKLL statement, that if you know the initial data on this pass,
So I would say that if you know the initial,
everything inside?
so the problem in HKLL, what happens is that there is a notion of normalizability that you're missing here.
Yeah.
So I don't have a precise analog of that. So, but I think the analog of normalizable versus normalizable is knowing the future and the past. So, and I think that how exactly it should be solved is, so one of the things that I'm doing with this.
Very sorry to, but there's also another difference, that your boundaries also extend in the bulk here.
Boundaries, HKLL, no, that part HKLL also has. Like if you have this, HKLL is basically this region is what you're talking about, right? So that part HKLL also has. So what HKLL does not have is this fact that its boundary splits up into this two null pieces. So so here in ADS on the other hand, you have this idea of normalizable, non-normalizable, because of which, if you know if you set the non-normalizable thing to 0, the rest of the stuff can be used to reconstruct, is the claim. So so here, what is the analog of that is probably a little bit more tricky.
Yeah, but just sorry, so I
Yeah.
should internalize HKLL a little more. But sorry, here it's clear in flat space that if you just knew the data past infinity,
Yeah, you can evolve it.
you're not going to be able to
You can evolve it, but I think
more to the point, you're not going to know what happens in
Right. So that's what I'm saying. That so there is a the statement, and there is a normal the non-normalizable piece has been set to 0 is a specific statement in the boundary, and I don't know the analog of that statement here. So, but I expect that it should exist. This is the.
Well, why do you expect it to exist? I mean,
Essentially because of the, like the statement that Shiraz was making early on, which is that you somehow expect to be like I mean, my rough picture is this, that I can foliate this with, the Einstein static will look like this. Like if you just say this metric, the standard, I'll work with 3 dimensions. So this at fixed R, these are what it is going to be foliated by. So and these are basically boxes. So I expect that if I put some, it's really kind of some sort of normalizability thing should exist, I feel.
But isn't it in very big conflict with what we expect from just bulk locality, that if you didn't tell me what the initial conditions going in through the other part of the boundary light cone is, how would I know what's going on?
It's at the historical final conditions.
Yeah.
Is that part of how you specify
Yeah.
the initial
These two.
Yeah.
So he's asking if you know this, everything about this, and everything about this, then can you?
Yeah. So it's basically the second order differential equation distributes its data in a different way here. So here it was,
all time like.
yeah.
But
Here it is a more. So, but yeah, I mean, while I think it is conceptually possibly, I do think there is a way to do it, but it's probably, the problem is technically I think probably different. And also I think it might be useful to do Lorentzian ADS CFT better also, I think. Because most of the things that people do seem to be much more in tune with Euclidean ADS CFT. So, but I think Lorentzian ADS CFT. No, I have, you have papers on this, I know that. no, absolutely, no, I mean, yeah. So, but my point is being that, like so I think there should be a better formulation of it. There's a paper by Marolf which I saw which kind of looked interesting using Schwinger, and I mean, we can talk about it later, but it looks, that I think could be adaptable even here. This is what I suspect. Because here, this note that the time slices are like this. So if you cut it off like this is in some ways, so the global Minkowski picture is, if you cut it off at some finite cutoff, so, and if you look at some two regions T1 and T2 between them, it's very similar to ADS in many ways. So I think the problem, the partial differential equation problem that one has to solve might be the same. And with a student, I'm actually looking at it right now, but we just started, so.
Even Chethan, I have probably some concern related to
Yeah.
what Sandeep is saying. So I have a hyperbolic differential operator here. So it's a Klein-Gordon equation. In Klein-Gordon equation, if I specify something in the past and the future together, okay, I'm over-specifying.
Right.
Perhaps what I'm doing is that.
No, but I'm not specifying everything at the past and future, right? So if you're saying that I specify everything here and everything here.
No.
Yeah.
Even if you specify the future past segment and the future segment, I think you are over-specifying. Maybe what you are doing is to specify phi minus pi below and phi plus.
Even in HKLL, yeah. So yeah, go on. Yeah. Sorry.
I'm saying,
That will not be enough. If you specify one piece of data on each, then you have to specify one piece of data surround. Roughly speaking, if you specify one piece of data.
Don't I expect to say that I specify half here and half there?
If you did it for all of scribe plus and all of scribe minus, that would be good. Half here and half there. But if you're doing it for part of scribe plus and part of scribe minus.
Yeah, that's what I'm saying. Yeah.
You'd have to surround it.
Yeah. So this part is unspecified.
Got it. Because there are past fellows with
Yeah.
visual sensors there.
Yeah. So it's not all over
Half
here.
and half is roughly like specifying both at the bottom, which is what Sandeep was saying. Which is not enough, because stuff will come in. He'll have to specify more than half and half. But I'd like to see how he does it.
No, but I don't have a way to do that. I just hope for the best at that stage.
So
The timeline trajectories, what's worrying me is, as you are drawing, there are timeline trajectories which never reach scribe plus or scribe minus.
Yeah.
How are you going to encode for that if you just give?
But you could say the same in ADS.
Yeah.
I know, so I haven't understood, but ADS is very special. Maybe it's tied to your normalizability issue and so on.
Yeah.
But because it's not obvious directly from bulk causality, I'm worried about your setup,
Yeah.
I'm not,
So yeah, I mean,
Just worried about
Yeah,
it.
I'll just give you an ADS response.
Yeah,
ADS response is if you stick to normalizable things, anything that happens there has a shadow on the back.
Has a shadow on the bulk. I know.
Has above it. So
I know.
he's
I know
hoping
it has a
somehow
shadow.
something.
yeah.
But that okay. I guess I don't understand the shadow story well enough to know whether it's going to work in Minkowski.
No, but in Minkowski's way, we could just solve the minimally coupled scalar equation
I know.
and do everything. Right?
Yeah.
Surely.
Yeah. But on the other hand, the way in which a useful set of holographic data can be kept is, while the amount of data that you need to specify, I think, is the same. It's not clear to me.
What is that? What does that statement mean? Amount of data is the same. How many functions do you need to specify on scribe minus on your bit of scribe minus r?
Good.
So I don't know how to do that in scribe minus and scribe plus, but I.
don't know how many.
So
One or two on scribe minus. You're not going to do it on scribe minus.
No. I'm saying that an approximation. If you say, let's say, a regulator for that is so if you put like a, this at some r equals some constant.
Yes.
So then I do have a I can demand that the functions that I get, the fields in the bulk are normalizable in that.
Wait a minute. So do you need to specify two pieces of data on your regulated surface? That's what I would expect.
Two pieces, yes, I have to specify two pieces, but one of them is basically zero.
However, you specify,
yeah.
there are two non-trivial pieces of data you need to specify.
That's right.
That
So
sounds reasonable.
yeah. So yeah. So that was the.
The way I'm thinking of it is that if we were doing the thing Dawson won't allow me to do, that is to evolve in space. Then this is the field at its first step.
Mm-hmm.
And then you evolve in space. That's
Right.
all kinds of crazy issues about that.
Yeah, yeah.
But roughly.
Phi and radial derivative.
Yeah. Fine. It's like grand factors
Yeah.
actually.
It's like a,
See, if you put a regulated, time-like surface, right?
Yeah.
Then what I would expect is for a well-defined initial value problem in the bulk, you need a good boundary condition, Dirichlet-Neumann or something on the time-like surface and initial data. And initial data. See, what is special about EDS CFT is that you just get away with less, right? But here, I'm not intuitively.
Yeah, so I agree with you. I agree with you that it is not, I just gave that as an example of saying that that's what one would like to do, if there was a regulator. But since, so my argument is basically just one of essentially looking at it in the sense that it looks like you can fix data here by having these two pieces of data. And the rest of it is, counting and rationalizing. But I think it is, how exactly one should do it is, I agree, it's tricky. It's a tricky question.
Well, it should be tricky at least for a minimally coupled scalar equation. You solve it, right? That's fine.
Yeah, but I mean, but his question of how to regulate it is somewhat tricky. So because so for instance, if I'm working only in this region, I need first a good coordinate system inside it, and the typical Rindler wedge would only cover this region. And these are minor issues, I agree in some sense, but they are issues nonetheless. So if you, on the other hand, if you slice it with the full Minkowski radial coordinate, and I put a box in the Minkowski this thing, then like Sandeep was saying, I need some data here in order to start evolving things. So there are, yeah.
Is there a standard Graham-Fefferman expansion from Sky Plus and Sky Minus?
I would love to have it, but
Isn't there one? What do all these asymptotic symmetry people do? What does Strominger do? What does Lara do?
yeah. So I mean, these are
Something like this must exist.
I don't know. But yeah, so I have never seen a clean, like if this is the first thing that I would like to have. So for instance, I have not been able to really see a discussion of just Minkowski with a radial cutoff. So just take Minkowski space and you have r equals constant. Just try to do like Witten GKP type of stuff in it. It seems like a very natural thing to try. Of course, you need to at least specify. The question is, of course, at least when it is Euclidean, I think it would be doable. If your time direction is Euclidean, I think it would be doable. If it is, if there is a Lorentzian time evolution, then there is a question of initial data and so on. But otherwise, it should be doable. But I have not really seen it. I have seen it for the Euclidean sphere, but not in the Euclidean cylinder. So yeah. So well, I mean, there are many things to say. Okay, so coming back to our picture, this slice has a simple description in terms of this symmetric asymptotic causal diamonds. And these are the ones that we are going to look at in analogy with the things that I was talking about before in ADS. Okay, so by translating these coordinates back to standard flat space means Minkowski with a radial coordinate. You can see that these asymptotic causal diamonds basically correspond to points of this type, where T and R are both going to infinity, but this T tilde minus R tilde is held fixed. So these are the points which end up becoming asymptotic causal diamonds. Okay, so explicit formulas are simple to write down, and we'll present one, which is this one, which is the claim that I made before, which is kind of intuitive, which is that these things should go to straight lines when your point is sent off to and your causal diamond is becoming asymptotic.
What's Q naught?
Sorry?
What's Q is controlled by Q naught?
Oh yeah, so Q naught is this guy. So as I was saying, these two, so this is the future and this is the past guy. So in a generic causal diamond, Q and P are independent, but if you take a symmetric one, so these are related by this, so P equals minus Q is Q naught, and then there is a one angle. I'm also making it symmetric. Okay, so in those coordinates, so this is basically Minkowski coordinates. So it's basically a straight line in Minkowski. This is what I was saying before. And as I said, this when R tilde, in the limit when R tilde and T tilde are going to infinity, while this is held fixed is the limit of these causal diamonds. So this is a finite quantity, and so you have basically a straight line at a finite distance from the origin of Minkowski space, and that's the boundary of these things. So yeah, so this is what we are going to use in what follows for brevity. So K is again, it's I think tan Q naught or something like that. So the asymptotic causal diamonds whose weights are defined by these straight lines. So this is the object that we are looking at, these guys or something like this. These are the things that we are looking at, and they can of course rotate because phi naught is still a movable parameter. So and this is a natural generalization of the Rindler wedge. So one can write down a Rindler-like coordinate system on it, and I claim that this is the natural coordinate transformation that will take you there. So it's like you can kind of see that by if you have a straight line like this and you're boosting in in the radial direction along this. So then this is the coordinate transformation that you have to do, and you will get some asymmetric. So so this is some sort of generalized Rindler metric, and so I haven't written the explicit form, but it doesn't matter. So the reason why you can call this generalized Rindler is because when k is 0 means that k equals 0 is so this q and p basically go from minus pi by 2 to pi by 2. So when q is 0, this is precisely this halfway up causal diamond, and that's what people call the Rindler wedge. Okay, so that's the thing that Rindler wedge in Minkowski space, and if you do this coordinate transformation on flat space, you will end up getting this guy here. So typically the Rindler wedge you talk about only T and R, but so if you have this extra dimension as well, you will basically get a time dependent type of thing. So of course it's flat space, but yeah, it looks like time dependent. And so yeah, so this is what I was just saying, which is that the asymptotic causal diamond has vertices that are halfway to time like infinity. That's the symmetric one, and that one precisely corresponds to this the standard Rindler metric. And yeah, so this corresponds to k equal to 0, and this is so a different version of this where this transformation, so this spherical Rindler space where so you shift this by so instead of k by cos phi, you shift it by a constant, then you end up having a spherical region of boosts around your origin of Minkowski space, and that's the case that people have studied for other reasons in the context of ADS-CFT, I mean holography. So yeah, so this is what I call my Rindler metric. But the thing I want to emphasize is that this metric, it's unlike. So let me erase this. Unlike in the case of flat space, this flat space means Minkowski space, where you have this R and this R are the same. So this is a spherically symmetric kind of thing. So which means that this coordinate R, R basically corresponds to a cylinder, right? So and that means that these 2 points are the same. But in the case of Rindler, this capital R, this guy also has this property. So if you transform it back to this conformal coordinates, what you find is that these fixed r's correspond to symmetric lines in r prime. R prime is my conformal coordinate, and that means that it covers only one region really. That's what it means. So I can either cover this patch or I can cover this patch, but I'm really covering only this patch. That's what it really means.
I've been spacing out the last two transparencies. Okay, correct. You're giving us the geometry of the bulk wedge labeled by 2 points. Is this right?
I didn't understand. Sorry.
You specified 2 points, one on Scry class, one on Scry.
That's you're talking about, yeah, exactly.
And then your this stuff in between is whatever you call it, and you're telling us about the geometry of that.
That's right.
Of course,
So
it's just a part of flat space.
yeah, it's a part of it's a part of flat space, but there are some technical issues in constructing this explicit bulk reconstruction.
Systems and so on. Okay, fine.
Huh?
Some coordinate system.
Yeah, so coordinate system, but yeah, I mean, I think they could be important. So
But what is the fundamental importance? You can always shoot GeoD6.
right, but so I would like to have a natural coordinate system that I can launch from here and come back or something like that. That is what I would like to have. So, but I can't really,
Can I ask this? Sorry, you can't launch a time-like geodesic from Scry minus or Scry plus, right?
No.
That's my basic problem.
No, you can't.
So how are you going to launch? I mean, if you're going to reconstruct everything by launching geodesics,
Yeah,
unlike in ADS, you can't launch any time. Like
I agree.
geodesics. So
Yeah.
So
So
how are we
it,
going to do it? How does it work? I mean, why do we expect it to work? Sorry.
I mean, I expect it to work because of essentially because of causality and the things that we were talking about before. But on the other hand, yeah, I think I think that maybe one has to have a cutoff at some point. So maybe that's the way to formulate it better. So yeah. Yeah, but I agree that I feel that that problem is somehow technical, or maybe there is a sense in which I think that the things inside here can be reconstructed from this. But I agree that it is, right now I can't defend it. Yeah. Okay, so yeah, so the technical or the coordinate system type reason why it is not is because of the fact that if you write this kind of a Riller coordinate system, it's only going to cover this region. So this region is not covered. So that's the explicit way in which something other than the standard Riller is required for do that if it is doable at all. So that's the thing. Okay, so I think I mentioned this already. So
why do we care about coordinates?
if I don't have coordinates, I can't explicitly do the calculation, right?
Fine, that's your limitation. But I use coordinates and so on. I mean patches. I mean, one of the lessons of general relativity is that we don't care about coordinates, right?
I agree. I mean,
we should be drawing some fundamental lessons.
I'm not drawing any fundamental lessons. I'm just saying that
It may make life tough if you can't do things.
Yeah.
But that's all you're saying.
That's all I'm saying. Yeah, that's all I'm saying. I mean, I'm happy to believe that this can be reconstructed. But since Sandeep was asking me how, and I don't have a concrete response. So, and the concrete response takes the form that I couldn't find any good coordinates. That's the practical reason. But I do think that there will exist a better way of thinking about it maybe, which will suggest a coordinate system. This is what I expect. So anyway, yeah. So this is what I was just showing here. This is this 1-to-2 nature. But on the other hand, for the full Minkowski, the r coordinate and r prime coordinate are 1-to-1. So the global, so in principle, I actually expect that some version of global reconstruction should exist. But then again, there is also the question of what boundary data should you put at, initial value data that you should put and so on. So that's another.
Could I ask again?
Yeah.
We know, take a minimally coupled scalar equation. We can solve it. We can do it in 15 minutes.
Right.
Okay. Then whatever boundary data is at Scry plus and Scry minus, you can read it out. And then check whether you can reconstruct, whether you can wiggle stuff here and not there. That will change the button.
See, the point is that at the very practical level, if you write it in terms of u and v coordinates, I find. So I'm again coming back to coordinates because to solve the equation in a useful way, I need coordinates.
But I mean, come on, you can transform. You can go to.
So for instance, if I take Einstein static, I find that this is a box that covers here. So my question is, where I have to cut off at some particular value of T and R, and then I'm again reduced to the question of initial value data versus boundary value data.
See, I'm not cutting off at all. I'm just solving in flat space. Minimally coupled scalar equation. This we all agree we can do. The ingoing and outgoing in spherical harmonics. We all agree we can do it.
Right.
Then you can go to any coordinate system you want. You have some nice coordinates inscribed plus, nice coordinates inscribed minus. You've got a well-defined question, right? Can you change the solution in the bulk without changing the solutions on those two boundaries? It's a completely well-defined question. Why can't you answer it?
I don't think that. I mean, that I think is not possible just by just general causality. But in an explicit solution, as an explicit way of solving, I'm not able to answer you.
And what is the general causality argument?
No, I mean it's just that I don't expect if I put data here and if that it should be enough. It's basically just that it's a causal diamond. That's really the answer.
No, but the causal diamond also has that in part.
Mm-hmm.
I mean, you're not specifying the data here.
Right. Right.
So what causality argument tells you that here and here is enough for here?
So if I have data here, I can evolve it like this and this.
Yeah, but that's the illegal evolution.
That is illegal evolution.
That's why you need a check. Right?
Yeah.
It's not clear the answer is yes or no.
Yeah.
But I think it sounds to me like it's an easy check.
That is what maybe we can talk after, because I'm not seeing this at all, because every coordinate that I write in, either if I work with u and v, it becomes a partial differential equation which I can't separate.
But suppose you go to polar coordinates, use radial. So think of Klein-Gordon equation.
Right, but then I cannot put good data here. I'll have to I'm putting data here, and then there is a question of what is the I'll have to cut it off with some t, and then there is initial value data here.
So you're saying that taking the cutoff surface to infinity
is the hard part. Yeah, I mean, at least I can't think of. Maybe there is a simple way, but Shira seems to be saying that. But I'm not. Whenever I do it with fixed,
I'm not understanding the difficulty. I can just forget your cutoffs. Your cutoffs are artificial, right? I can solve this thing in the whole space, and then any question you have is a sub part of my question, because I've given you every possible solution. Then you can put whatever boundary conditions you want. I've just found every solution of Klein-Gordon equation in flat space.
Yeah. So yes. That's actually, yeah, so maybe I should, but the thing is, I don't know whether there is all of these things, I'll have to specify how I am approaching the T and R, no? So
do it all later. First you find every solution.
So every solution is easy to find, at least in TR, this thing I can find it, yeah.
Totally easy.
Yeah.
And then if you've got a clear question, you can answer it, right? I mean, I can't see the difficulty, but we can talk about it.
No, but so what would be the precise question? Can you?
I think the question would be, and to answer all the questions that have been raised, is can you find a solution which has identical behavior here and here, but differs here? Two solutions which are identical on those two regions, but differ somewhere in the bulk. That's the question of bulk reconstruction, right?
So you're not, yeah.
In particular, can you find a solution that is 0 there, but non-trivial somewhere in the bulk?
Yeah, I think that answer would be no. But I was hoping to do that an explicit reconstruction. So I guess that's not what you're asking at all.
This is the first question.
Okay.
Then the second question, since you have every solution, you could also do that, right? Like some Green's function business. It seems to me. I don't know. I mean, I don't know what the difficulties actually arise when you start putting pen to paper, but
yeah. So I mean, the basic problem is only that the general solution is basically a sum of these things in T and R and phi. And then when I try to actually go to the UV coordinates, I get, it's basically a sum expressed in terms of T and R and phi. And then I am trying to go to U or V, and then I run into trouble. This is what I didn't push it very hard. This is also true.
I was trying to do in my head, I'm also not able, but for a massless field.
For a massless field, many things could be easy. And the equations are straight. Yeah. Yeah. I agree.
Yes.
Yeah. In massless
field is where I'm worried.
That is exactly where the problem is, because that's where that's exactly where the problem, because the equation, that's precisely where the equations are not separable in UV. Yeah. So I have to also say that I have not tried very hard. I haven't tried very hard, so maybe Shiraz is right. So anyway, so okay, so again coming back to the geometry of these things. So yeah, so the where was this? What is this? Yeah. So so I would like to to answer the previous questions. I mean, I was the question about the geometry of this thing. So the question was, how exactly does it look in conformal in the conformal coordinates? And this is the form that it takes. It's easy to see. And I'm just writing down the equation for the big circles, the great circles of the sphere also here, just for comparison. But this is our curve, and but noting that the similarity of the two forms suggests an easy way to compare this. I mean, I'm just saying coordinate stuff. It's not important. So finally, you basically get that this is the form of your curves on the Einstein static sphere, where the x, y, z are the embedding. So I have an Einstein static sphere, and I'm writing it in terms of this x, y, z. Okay, so so these I can plot this way. So this is the sphere, and if phi naught is 0, so it will basically slice in this way. And so this answers Sandeep's question. Basically, these are circles that go around like this. So this is what these are, and I can, in principle, rotate this whole sphere. So yeah, in this way. So yeah, so it's so I think if there are any questions about the geometry, I think this should answer it. Okay, so yeah, so again, so I should draw one more picture here. So this is in r prime coordinates, which is the conformal coordinates, and so this is the shape of, for example, the causal diamonds would take, and another one would be, let's say, like this. So they always go from diametrically opposite points, and there's a shape of these curves. You know, I'm not vouching for them, but the point is that they will go from here to here, and there will be some minimal distance from the origin that they'll have, and they're going to touch the boundaries here. So this is the cross section. So whatever is inside here is the cross section of, this is the causal diamond that, you know, has some point which is a vertex here. So this is the idea. Okay, so any questions? I was only talking to the faculty, so if any students, you know, this geometry is, you know, like this is completely simple. So if you have any questions, please do ask. So okay, so this is natural because the straight line, yeah, so I have explained that there. And so effectively the picture, so this is, so a causal diamond would basically look like something that is inside, it will have this shape, and that's the regions that I've drawn of the boundary, and the solid region covered by this green thing, and the same points, they will have something on the cone, and the region between them is basically the causal diamond. Okay, asymptotic causal diamond.
Is the analog of not having normalizable, having no outgoing stuff for the scribe minus?
This is what I was thinking. Yeah. So this is one of the things that I was. Yeah. It's like, I think it.
On scribe minus?
I don't know
that. Be traveling along this but from here you just send stuff in. In the past, stuff goes in rather than out.
Yeah, so I really should try to solve it properly. I should have. So, but so the reason I'm fairly confident conceptually it will work is because it's I mean, maybe it's still, the counting of functions seems the same, the causal structure seems fine, and this you know, this kind of schematic argument where you put data here and illegally evolve it, it seems to fix it. So because of these reasons, I think it is, you know, there should be a way to do it explicitly. Okay, so now I'm going to talk about this quantum error correction business. I, again, don't know much about it, but I will say, so the things that I need are just one essential statement that these guys make, which is that the reconstructed bulk region from these Rindler wedges have a certain intersection and union structure. Okay, so this is the thing that, so this is the thing that we would like to reproduce here. And there, you know, we will be able to reproduce it, but there is a major caveat as well, which I will talk about later. So, so the idea is that, so what we do is, so of course, so what we do is we just put like if you just put a cutoff in some finite radius on this, so the regions that are cut off by the causal diamond will be so of this form. So this should be compared to the standard picture that people have in these things. So let me just draw the third one, which is, this is a typical picture that people draw in the context of this quantum error correction. The idea is that there are some boundary regions A, B, and C, and there is some bulk point in the center which we would like to reconstruct. And if you have just A data, you can't reconstruct. If you have A and B, you can reconstruct it. And if you have all three, of course, you can reconstruct it. So erasure of any one boundary region, you still are able to reconstruct the bulk region. And that structure you can see is immediately there even in this structure. It's just that the boundary curves have changed their shape. So that's all that has happened. So yeah, so the shape of the bulk, but the shape of the bulk reconstructed region has changed. In flat space, they're bounded by straight lines. But as long as the cutoff is finite, the union intersection structure remains intact. And the cutoff being finite is, I'll have a little bit more to say about that. I think that's where the baby is getting thrown with the bathwater.
Sorry, just one last
Yeah.
This not having outgoing stuff that's prime minus is probably equivalent to saying that spatial infinity is nothing happens then.
Spatial infinity, yeah, it could be. That's, yeah.
Because if you've got outgoing stuff that's prime minus, it ends up at spatial infinity.
Right.
And you know, if your boundary condition is that as you go just in space and nothing happens, then that will forbid that.
Yeah. So,
So it might be related to the stuff Strominger keeps talking about putting boundary conditions at spatial infinity. You know, so when you put particular boundary conditions at spatial infinity, that's what allows you to tie up scri minus and scri plus. So it may be another way of saying that.
right.
What will be another?
That you're forbidding outgoing stuff at scri minus or ingoing stuff at scri plus.
Yeah.
Outgoing means along.
Along. Because you see, if it's outgoing at scri minus, it'll end up at spatial infinity. Or if it's ingoing at scri plus, it will have come from spatial infinity.
Yeah.
Now, in Strominger's way of thinking of this stuff, it was, you know, he had a map between scri plus and scri minus. It was totally crucial for him that spatial infinity was very tame.
Right.
This is probably the same thing, the same state. So maybe that's the maybe the analog of talking the normalizability is basically some statement about spatial infinity.
That was about all of scri minus to all of scri plus. No.
He wanted to make a map.
Right. So then, so that's like specifying the A daggers below and A's above.
Yeah.
But he is now limiting, part of scri minus and part of scri plus. So therefore, I don't see that picture.
Yeah. No, I agree. He's doing much more. I was just trying to understand what the analog of normalizability. You know, in ADS we specify that something is normalizable and we specify its first form. So those are the two conditions. You're saying that this will not be enough. You're probably I'm not sure.
So, but I think that will be the difference. The precise analog exists also in ADS, because in ADS the analog would be the difference between global reconstruction versus Rindler wedge reconstruction. So, if an analogy exists at all, then I would imagine that the analog of Rindler wedge is precisely this. So what so the question of even in a Rindler wedge, you have this possibility of normalizability versus non-normalizability, and if you kill off the non-normalizable guy and specify data in terms of the normalizable one, then you can reconstruct. So
You're saying in ADS there is a limited version of Itham and Graham,
yes,
which allows you to
yes,
sort of
precisely.
data
Yeah, that is the whole, that is the thing. Yeah.
Like Poincaré Apache.
Yeah.
Right.
Yeah.
Like Poincaré.
Yeah. So
Good. I see.
it's really from a bulk subregion. I'm sorry, boundary subregion. You can construct this causal wedge part. That's the thing. Okay, so so I think I said what I kind of wanted to say regarding that. So this, because the slides are very new, I can't really remember what I said in the slides. Yeah. So I'm just drawing the same thing in the conformal Einstein static coordinates, but it's not super important because since here it works, it must work here as well, as long as you have a cutoff. And note that the cutoff is essential for this. So so the same picture holds. And another fact is that as the tip of the causal diamond moves up towards the vertex of your Minkowski causal diamond, the region that you can reconstruct from the boundary, it becomes the entire bulk region. So, and that is also exactly analogous to what they have in ADS. And a crucial ingredient here is that in the case of ADS, people expect so half of the boundaries region should be able to reconstruct the center. This is something that you would like to have because of general statements about erasure protection of error correcting codes, because you have to have enough number of extra bits in order to forbid erasure, and I think it is half of the total Hilbert, half of the total number of qubits. So that same picture applies here as well. Yeah, so this I think I already said. Yeah, so it will be nice if one can reconstruct this in terms of if you put a cutoff here, and you can, so effectively what it is doing is that it is putting some sort of a causal structure on the Einstein static space that is there at a finite cutoff. That's what it is really doing, and that's its R cross S1. This R cross S1 is, this Einstein static should not be confused with the conformal Einstein static universe that is mapped from the full space-time itself. This is just the boundary of this. And yeah, so that's one statement. So now let me emphasize a caveat, which is that the crucial difference in ADS is that the subregions themselves are ultimately, unlike here, the subregions themselves are ultimately scrambled versions of each other. And the reason for that is that if you, let's say you are, so a straight line here and something that did not intersect. So these two regions are independent here, but if you expand the cutoff, you see that this region has an overlap here. Okay, so that's tied to the fact that so this means ultimately that so in ADS what happens is that you have some place where you can just go and stand, and then the tensor factorization of the Hilbert space is God given. So you can so the boundary subregions are boundary subregions, the causal structures are completely fixed and everything. And so here on the other hand, that's not quite the case, because you can see that you can do this, if you put a cutoff and you do this thing, there exists the analog of this code subspace business in here, but so what gets called as a subregion here is ultimately, in the full theory, it's in some sense scrambled versions of they can be scrambled versions of each other. So there is no canonical final boundary subregions that you can assign, and that's, I guess, expected because we are working with flat space. Where was it? Yeah, okay. So I think that's basically the main statement. So as previously stated, the space-like straight lines that bound our asymptotic causal diamonds should be compared to the space-like bulk geodesics that were used to define CFT kinematic space. And in flat space, since the conformal boundary does not have a well-defined causal structure, this perspective needs change. And our proposal gives a natural bulk construction of the boundary kinematic space, and that's really what this is. So the idea is that to give a kinematic space a cutoff, and so we have given a bulk construction of the boundary kinematic space as long as you have a cutoff. So this is what is really happening. And
bulk construction of the boundary, but didn't you also give a bulk construction of the boundary kinematic space without a cutoff?
So yes, I mean, so yeah, I mean, yeah, absolutely. So every straight line is basically that. Yeah. So, but I'm just saying that.
You've also done.
Yeah, yeah. So I mean, it's a minor statement. Yeah. So, but that is the one that is crucial for reconstructing the bulk stuff in the sense of this quantum error correction business. That was the only point of that. Okay, yeah, it is noteworthy that the space of suitably chosen pairs of points seems to have a natural role in flat space as well. So this is so this idea kind of generalizes. It's kind of something that I kind of find interesting. Maybe in order to covariantly define some, subspace, the tensor factors of the holographic data or holographic Hilbert space, this might be a way to go about it. So yeah, so these are some analogous observations that one can make. So since I don't know whether people are, yeah, so there are things which are people done with kinematic space, which we expect that we should be able to do in flat space as well. So this is the these are the some things. I mean, I'll just flash the slides, fine. If you have questions, you can ask me. So a completely related statement, which is that these lines, obviously these are the minimal surfaces of flat space, and you can construct, the idea of Ryu and Takenagi of using these as minimal surfaces and trying to show that you can immediately show that these also satisfy strong sub-additivity and all that, because it essentially follows from what is it called, triangle inequality, that type of stuff, okay, in the bulk.
In this series, how are you defining theory entropies of the boundary regions?
That's an excellent question, and let me slightly rephrase the question in the sense that the boundary entropy is going to scale with volume here. So, and that is ultimately, I think, tied to the fact that your theory, that the ultimate theory that is, that is giving you the S matrix or whatever, is non-local. I think that's probably the way to understand it, I think. Or maybe, well, I mean, yeah, maybe we can talk afterwards. So, yeah. So that again is tied to the fact that if you as you take the cutoff farther and farther out, if at a fixed cutoff you have these subregions that are completely well defined, but as you move the cutoff out, I think that they get a reinterpretation as scrambled versions of each other. So that
Here it fits in the same notion of entropy as in classical entropy, in the sense areas of the cutoff. Whatever amount of T mu falls to it.
No, here what we have defined is really if all we have defined is a holographic definition of entanglement entropy or minimal surfaces, which we claim is, not just me, other people have also done that, which has the one thing we can notice is that it has a strong sub-additivity and it is a minimal surface. So these are two facts we can look at, and then we claim that this is some kind of a holographic definition of entanglement entropy in flat space. But if it is a holographic definition, it should be of some holographic theory, and that theory's area entanglement entropy scales with volume, and so it's not really kind of like a standard quantum field theory, let's say. So
this does not use this, but there is this notion of that at the asymptotic infinities you can define a 2D field theory just by using the angle coordinate.
yeah, it might. So there is.
I'm saying your construction does not use it necessarily. It just says that.
So for instance, if you do the cutoff with if you do the Einstein static cutoff, Minkowski space and do field theory there. So for instance, I was trying to do correlation functions in some simple-minded ways on the boundary, and then you see that if you so there is a possibility that ultimately the correlators will have a bulk Poincare invariance, but in the limit when the cutoff goes to infinity. But you'll have to scale things. You'll have to scale things in an appropriate way. So, and that we have not been able to fix yet, but I suspect that there is a way to do it. So yeah, so then there will be a sphere. The correlators will be on the sphere. So, but yeah, I mean, again, that is all part of the work in progress banner. So, but yeah, it's one would hope that it will go in that direction. That's right. Okay, so yeah, so this is what I just mentioned, and yeah, so there's more speculations if you want to set. Bulk reconstruction from the something like black hole horizon. Can we do that? Like, because you can also, if you have a Penrose diagram of, let's say, even flat space, or doesn't matter really. So you can attach causal diamonds here as well, and then there is some notion of reconstructing the bulk by putting data at the horizon. So in some sense, so yeah, so there could be a few things that can be said there, and
just a comment, in fluid gravity you can.
Right.
In fluid gravity,
Right.
with the fluid gravity boundary conditions.
Right.
This is perfect.
So, and the stretched horizon is basically the analog of the R cutoff that we are putting in the boundary. So yeah, so there is a precise analog on this side as well. So yeah, so
That's because in the derivative expansion, it doesn't go outside of
It
the
doesn't
tube.
do that, yeah.
The tubes, the null tube.
Yeah, going this way is, yeah, exactly. Go like this. It's actually, our regularity condition is precisely the condition, analog of the condition that there are no waves going like that along the horizon. That's exactly like what I was saying on stripeless.
I see.
But it becomes local because of the tube theory.
So there it's totally manifest.
Okay, so yeah, so there is so a few more speculations, and then I think that's the end of my talk. Thank you.